Section: Introduction. In this section, we discuss how artificial intelligence, AI, is transforming industries and everyday life, primarily due to the rapid advancements in large language models, LLMs. Initially, the focus on AI's environmental impact was on the energy-intensive training of models. However, as generative AI applications gain popularity, attention has shifted to the energy and resources used during model inference and serving. With AI models responding to billions of user requests worldwide, the energy consumption, carbon emissions, and water usage associated with these responses have become significant contributors to AI's environmental footprint. To address this, various research initiatives have emerged to measure the energy used per prompt. Early studies provided rough estimates based on general assumptions about hardware and model characteristics. More recent efforts, like the AI Energy Score and ML Energy benchmarks, have improved accuracy by using direct measurements on standardized hardware for specific tasks. Additionally, some studies have looked at the carbon emissions and water usage linked to AI model serving. Despite these advancements, we still lack first-party data from major AI providers. Drawing from our extensive experience in large-scale software deployment, we offer insights into the operational realities of managing a global AI production fleet. To effectively assess and optimize the environmental impact of AI model serving, we need a thorough understanding of energy consumption, which includes the power used by the CPU and memory, energy consumed by idle systems, and the overall data center energy efficiency as indicated by the Power Usage Effectiveness (PUE) metric. The absence of a clear consensus on what to include in these measurements has led to significant variations in published estimates for similar AI tasks. In this paper, we present a framework to measure the energy, emissions, and water impacts of a production AI product at Google. We propose a comprehensive measurement approach that considers all relevant energy sources. We apply this methodology to Google's Gemini Apps product, providing the first analysis of three key environmental metrics: energy per prompt, emissions per prompt, and water consumption per prompt. Our findings reveal that existing measurement methods often overlook important energy consumption activities related to AI serving. We also demonstrate substantial efficiency improvements over a year, resulting in a 44-fold reduction in emissions for the average Gemini Apps prompt. Establishing comprehensive environmental metrics is essential for promoting efficiency across our large-scale AI operations. We categorize existing efforts to quantify the environmental impact of AI inference into two main approaches: model-based estimation and empirical measurement. Early studies relied heavily on estimations based on publicly available hardware specifications and assumptions about usage patterns. While these theoretical models highlight the potential scale of the issue, their results can vary significantly due to the sensitivity of the underlying assumptions. In contrast, recent initiatives have focused on empirical measurements, using software tools to directly assess energy consumption during specific tasks on standardized hardware. While this shift has improved precision, differences in methodologies still hinder comparability between studies. We also note that model-based estimations of AI inference environmental metrics are common but vary widely due to their reliance on uncertain input assumptions. Some notable studies include estimates of energy consumption for various AI models, with results ranging from around 0.3 to 3 watt-hours per prompt, depending on the model and assumptions used. This variability complicates our understanding of the environmental impact of using AI assistance and limits our ability to implement effective reductions in environmental impacts. Section Summary. In this section, we highlight the growing environmental impact of AI model inference, emphasizing the need for comprehensive measurement frameworks to accurately assess energy consumption, emissions, and water usage associated with serving AI applications. We propose a full-stack measurement approach and apply it to Google's Gemini Apps, demonstrating significant efficiency gains and the importance of standardized metrics for incentivizing sustainability in AI operations. Section: Measured Metrics. In this section, we discuss the measured metrics related to energy and emissions from AI accelerator hardware. We note that 4 main studies have directly assessed these metrics, but they differ significantly in their measurement methods, making comparisons challenging. For instance, Laccioni et al. In 2022 estimated the energy and emissions for the Bloom model during inference, using the Code Carbon library to account for energy from GPUs, CPUs, and DRAM. They found an average of 4 watt-hours per prompt and 1.5 grams of CO2 equivalent per prompt over 18 days of inference without batching. Samsi et al. In 2023 benchmarked various sizes of the Llama model on 2 types of NVIDIA GPUs. They reported that the Llama 65B model consumed about 0.3 watt-hours per response. The AI Energy Score initiative focuses on empirical benchmarking and direct energy measurements on standardized hardware, specifically NVIDIA H100 GPUs. They use Code Carbon to measure GPU energy and aim to create a comparative star rating for energy transparency, although they limit the inference batch size to 1, which may not reflect real production environments. The ML Energy Framework also uses empirical benchmarking with production-grade hardware like NVIDIA H100s, emphasizing real-world conditions, including steady-state operation and batching. They measure GPU energy with the Zeus library and aim to provide accurate per-request energy figures. We recognize that the transition from model estimation to empirical measurement enhances accuracy and transparency, but the specific boundaries of these measurements are crucial for interpretation. For example, 2 different measurement methods found a 6-fold difference in energy consumption for Llama 3.1, highlighting the variability in results. As we explore in this study, large-scale inference systems can differ significantly from existing benchmarks. The efficiency of AI accelerators directly affects energy consumption, and large-scale systems aim to maximize this efficiency. We outline several approaches to improve AI serving efficiency, many of which have been pioneered by Google. 1. Batch inference. This allows multiple prompts to be processed simultaneously, optimizing accelerator usage. Smaller batches reduce latency, while larger ones enhance throughput and efficiency. 2. Speculative decoding. This technique uses a smaller draft model to predict results, which can skip steps in the larger model if successful, leading to more efficient inference. 3. Disaggregated serving. By separating the prefill and decoding processes across different accelerators, we can optimize each step for better performance. 4. KV caching. This saves intermediate results from the attention mechanism, reducing redundant calculations when generating subsequent tokens. 5. Optimized software-hardware stack. This involves making efficiency improvements across all layers of the serving stack, such as using Google's XLAML compiler and other systems to enhance model computations. Our study aims to provide a production fleet perspective on the realities of serving AI products. We seek to define environmental metrics for AI serving that allow for meaningful comparisons, set broad standards for measurement, and encourage optimization of energy-consuming activities. However, we acknowledge that our contribution does not cover all aspects prioritized in previous studies, such as controlling for hardware differences or ease of measurement. In our methodology, we propose a comprehensive approach to measure energy usage, emissions, and water consumption for serving AI models at scale. We believe this approach can establish a consistent standard for measuring carbon emissions in AI serving and align incentives for reducing emissions. Our methodology consists of 4 parts. 1. A clear measurement boundary with transparent exclusions. 2. Energy measurement methods. 3. Emissions and water measurement methods. And 4. The selection of an aggregate representative metric. Section Summary. In this section, we review various studies measuring energy consumption of AI accelerators, highlighting significant differences in methodologies that affect comparability. We propose a comprehensive approach to standardize measurements of energy usage, emissions, and water consumption for AI model serving, aiming to establish consistent metrics that encourage emissions reduction and optimize energy efficiency. Section: Measurement Boundary and Exclusions. In this section, we define the measurement boundary, which outlines the activities included in our metrics. Specifically, we focus on energy-consuming activities related to serving large language models, LLMs, which contribute to emissions and water use. Our measurement boundary encompasses energy sources that Google can control, meaning we can implement changes to behavior. We consider one serving AI computer in a data center as our functional unit. This includes one or more AI accelerator trays connected to a host tray. We break down energy consumption into several categories. 1. Active AI accelerator energy. This includes the energy used by all AI accelerators connected to the active AI computer, covering tasks like pre-filling and decoding. It also accounts for the energy used for communication between accelerators during operation. 2. Active CPU and DRAM energy. The CPU and DRAM in the host tray are essential for running the accelerators, and their energy consumption is included in our metrics. 3. Idle machine energy. To maintain high availability and low latency, production systems reserve capacity that may be idle at times but is ready for traffic spikes. We include the energy consumed by these idle AI computers, which are necessary for service reliability. 4. Overhead energy. This refers to the energy used by data center infrastructure, such as cooling and power conversion systems. We capture this through the Power Usage Effectiveness (PUE) metric. We also note some exclusions from our measurement boundary. Networking. Energy used for external networking is excluded since we lack control over it, and data center networking energy is minimal for AI prompts. End-user devices. We exclude energy consumption from end-user devices due to a lack of operational control. LLM training and data storage. Our study focuses on the energy used for inference and serving AI prompts, leaving training measurements for future research. For our energy measurement methodology, we developed a comprehensive approach based on internal telemetry from Google's AI serving fleet. This involves identifying all LLM models serving the Gemini app and mapping them to job and machine IDs to measure energy consumption during inference. We collect power measurements for the host and AI accelerators and track the total time each machine is allocated to a job, including idle time. We define energy components based on these measurements, including total energy, overhead, idle, active CPU and DRAM, and active AI accelerators. We also measure the total user prompt count across Gemini Apps products for each LLM model. By dividing each energy component by the total user prompt count over the same period, we calculate energy per prompt, measuring over a day or longer to ensure accuracy. In contrast, we define an existing approach that focuses on a highly utilized benchmark on a standalone AI accelerator. This approach measures only the energy of active AI accelerators and uses data from the top 10% most energy-efficient data centers, allowing for a more direct comparison with existing literature. Section Summary. In this section, we define the measurement boundary for energy consumption related to LLM serving, which includes active AI accelerator energy, CPU and DRAM energy, idle machine energy, and overhead energy, while excluding external networking, end-user devices, and LLM training. We also outline our comprehensive approach for measuring energy metrics using internal telemetry, contrasting it with an existing approach that focuses on a narrower scope for better comparison with existing literature. Section: Emissions and Water Metrics Methodology. In this section, we outline our methodology for calculating emissions and water metrics. We generate carbon emissions based on the energy mix of the electricity we consume and the emissions from our computing hardware. We calculate the carbon emissions for our large language model, LLM, services using the average annual grid emission factors from the previous year across our data centers, following market-based standards. Market-based emissions consider the emissions from the sources of electricity we purchase, allowing us to account for carbon-free energy purchases that help reduce our emissions. In contrast, location-based emissions focus on the emissions within a specific area, excluding the effects of our carbon-free energy procurement. For our analysis, we use market-based emissions. For 2023, our location-based emission factor was 366 grams of CO2 equivalent per kilowatt-hour, and the reduction from our carbon-free energy was 231 grams, resulting in a net market-based emission factor of 135 grams. In 2024, the location-based factor was 345 grams, with a reduction of 251 grams, leading to a net market-based factor of 94 grams. We use the previous year's average emissions factors since we publish these metrics annually. We emphasize the importance of including full lifecycle emissions, which encompass both operational and embodied contributions. While it is uncommon to include embodied emissions in the literature, we do so to provide a comprehensive measurement. Regarding water consumption, our data centers use water for cooling to minimize energy use. We measure water efficiency using the Water Usage Effectiveness (WUE) metric, specifically focusing on consumptive use, which accounts for the water that is evaporated and not available for reuse. On average, we consume 80% of the water we withdraw. We calculate the water consumption for our LLM services based on energy per prompt, using the previous year's average WUE value, which was 1.15 liters per kilowatt-hour for both 2023 and 2024. We aim to define aggregate metrics for energy, emissions, and water that reflect typical user behavior and can be compared over time. However, we acknowledge the challenges posed by the rapidly changing AI landscape. We observe that the distribution of energy per prompt can be skewed, influenced by a small number of prompts that either have low usage or high token counts, leading to disproportionate energy consumption. The arithmetic mean can be heavily affected by these outliers, so we use the median as a more reliable measure of typical user impact. To calculate the energy consumption for the median text prompt on a given day, we first find the average energy per prompt for each model and rank them accordingly. We then create a cumulative distribution to identify the model serving the 50th percentile prompt. The average energy per prompt is defined as the energy of this median prompt, and we calculate the monthly median similarly. Finally, we derive the corresponding carbon emissions and water consumption using the conversion factors established in our methodology. In the results section, we present the environmental impact metrics for our Gemini Apps AI Assistant, comparing our comprehensive methodology with a narrower existing standard. The findings reveal significant differences between the two approaches, highlighting the need for a thorough measurement framework. Section Summary. In this section, we outline our methodology for calculating carbon emissions and water consumption associated with LLM serving, emphasizing the use of market-based GHG emissions and the Water Usage Effectiveness metric. We also discuss the challenges of defining aggregate metrics due to the skewed distribution of energy consumption, advocating for the use of median values to better represent typical user behavior and environmental impact. Section: Gemini Energy Consumption. In this section, we analyze the energy consumption of Gemini apps. Using our detailed measurement approach, we find that the median energy used for a text prompt in May 2025 is 0.24 watt-hours. Our data shows that most of this energy, 0.14 watt-hours or 58%, comes from the active AI accelerator, while the host CPU and DRAM account for 0.06 watt-hours or 25%. Idle machines and data center overhead each contribute 0.02 watt-hours. This indicates that we would need to scale the active AI accelerator's energy consumption by 1.72 to account for energy used in a production environment, which is less than the previously estimated factor of 2. When we apply a narrower measurement method, we find the energy consumption drops to 0.10 watt-hours per prompt, reflecting a more limited scope and higher machine utilization. Our comprehensive method reveals that the total energy consumption is 2.4 times higher than the narrow approach, highlighting the need for standardized measurement practices that encompass all energy-related activities. Both methods yield lower energy consumption figures than many previous studies. Next, we consider emissions and water usage. While energy per prompt is crucial, the environmental impact is ultimately determined by emissions and water consumption. Google's initiatives to reduce emissions and water use have significantly lessened the environmental effects of AI services. Our comprehensive measurements show that a median Gemini app's text prompt generates 0.03 grams of CO2 equivalent and uses 0.26 milliliters of water. These figures are even lower with the narrower approach, at 0.01 grams of CO2 equivalent and 0.15 milliliters of water. To put this in perspective, 0.24 watt-hours is less energy than watching a TV for 9 seconds, and 0.26 milliliters of water is equivalent to 5 drops. Our 2023 Water Risk Framework ensures that new data centers in high-stress areas will use air-cooled technology, which we expect will significantly lower water usage over time. Improvements in energy efficiency and water usage will further reduce the environmental impact of AI prompts. The breakdown of emissions shows that electricity-related emissions are the largest contributor, indicating that enhancing energy efficiency and decarbonizing electricity are key areas for impact. We also track emissions efficiency gains. Our comprehensive measurement of AI-serving metrics allows us to monitor and encourage optimizations. From May 2024 to May 2025, we achieved a 44-fold reduction in emissions per median Gemini app's text prompt. This reduction stems from a 33-fold decrease in energy consumption due to software efficiencies, including a 23-fold reduction from model improvements and a 1.4-fold reduction from better machine utilization. Additionally, we saw a 1.4-fold decrease in emissions intensity from our data center electricity and a 36-fold reduction in overall emissions per prompt due to fewer machine hours. We anticipate these efficiency gains will result from several efforts, including smarter model architectures that enhance efficiency significantly, efficient algorithms that reduce energy use without sacrificing quality, and optimized delivery of AI models. Our custom-built hardware is designed for high performance per watt, and our latest generation of TPUs is 30 times more energy efficient than earlier models. We also optimize idling by dynamically managing model demand and utilize an advanced ML software stack for efficient computations. Our data centers are among the most efficient in the industry, and we continue to pursue clean energy procurement to support our carbon-free goals. Despite increased electricity consumption, we have managed to reduce our emissions, demonstrating a decoupling between energy use and emissions impact.